Am I audible? Okay. Uh, Good evening, everyone. Today is the 11th NPTEL PMRF interaction session on design of steel structure. My name is Devashish Panda. I am a doctoral student and Prime Minister Research Fellow at IIT Guwahati. Okay. So let's start the session quickly. So during the last interaction session, we learned how to design the laterally supported beams. So today, first, we will visit this section of laterally unsupported beams, how to design them, and then we will move to, we will spend some time on how to calculate the section modulus. Then we will move to the design of purlins, where we will learn the design procedures of that I section and channel section, as well as the angle section used as a purlin. Then if time permits, we will go to gantry girders and we will solve. Before that, we will solve the previous year assignments. Okay. So first, laterally unsupported beams. So on the last class, we have seen that for the laterally supported beam, what should be the possible design procedures and the checks, right? So let first today, one second. Okay, so laterally unsupported beams, right? The thing is, what? Uh, okay, uh, I think there is a slight internet problem. Okay, no problem. Okay, so what I saying about the laterally unsupported beam. So in the case of laterally supported beam, what we have seen that the beam is generally supported on the lateral direction by means of bracings or any kind of laterally supporting members. But in case of laterally unsupported beams, the lateral supports are not provided. So we have seen the design procedures and steps for the laterally supported beam. So what should be the laterally unsupported beam? How we can design the laterally unsupported beam? So today first we will go into it. So clause 8.2.2 actually deals with the design specifications and requirements of the laterally unsupported beams. Okay, so first thing we have to know or understand how to calculate the design bending strength for the laterally supported and laterally unsupported beams. So laterally supported cases, we have seen that first we need to calculate, or first we need to find it out that the beam section or the section whatever we are designing, first we need to find it out that is it under low shear or high shear, and accordingly as per IS 800 we can calculate the design bending strength. So for the laterally unsupported beam, clause 8.2.2 gives the expression for design bending strength. So what that expression said, the design bending strength of a laterally unsupported beam can be calculated using this formula. And what that formula said, first part of the formula beta b, that is nothing but a factor which deals with the sectional property, right? So if the section is plastic or compact, then the beta b value will be 1. Otherwise, we need to calculate the beta b value as per the ratio of ZE, elastic sectional modulus, divided by the plastic sectional modulus ZP. Okay, now ZP in the second term of the equation ZP. So it is nothing but the plastic sectional modulus, which we can easily calculate, or these values are provided in SP6 or any kind of handbook. Now the thing here, FBD, what is that FBD here? So FBD, what I say for the laterally unsupported beams, that they are not supported on the lateral direction. So there is a possibility of the lateral torsional buckling. Here you can see what is the lateral torsional buckling. That is nothing but for the long beams, what happened for the case of long beams, then then if they are subjected to bending, then there is a possibility of lateral buckling like this. So to counteract lateral buckling in the term of FBD, that means the design bending compressive stress. So here that term of lateral buckling strength is included. So how the thing is, these two values we can easily calculate here, but for the calculation of FBD, the design bending compressive strength, how we can do that. So here two procedures are there. Either we can follow the equations, like FBD can be calculated using this equation, chi LT Fy by gamma m naught, where that chi LT value can be calculated using this formula. Now to calculate the chi LT and other values, we need to know the alpha LT value. What is that alpha LT? That is nothing but the imperfection parameter, and the value of this will be 0.21 for a rolled steel section and 0.49 for welded section. So using this formula, set of formulas, and we have one formula that M shear, so we can calculate the value of FBD. And one more thing, we have one procedure we have by which we can easily calculate the value of FBD, and that is the table. So from here, the table number, we can see that table number 14, we can calculate the F shear B value first. So the value of F shear B depend upon lambda, that means KL by RY for this particular section. If we can calculate the value of this, and if we know the height or overall depth H by TF ratio for a section, particular section, if we know these two parameters, then from the table 14 we can easily calculate the value of what? FCRB. Okay. Now, if we can calculate the FCRB value, now depending upon that FCRB and FOI value, and also alpha LT, that means we are using the rolled section, so we can calculate the value of FCRB easily from the table number 13A for the rolled sections. Okay. So from table 13A, we can easily find it out, the value of FCRB depending upon the value Fy, that means the yield strength, and FCRB value. So we can calculate from this table, we can calculate the FBD value. Now, once we know the FBD value, now we can easily calculate the design bending strength for a laterally unsupported beams using that MD is equals to beta B ZP into FBD. So the FBD term was the unknown term for this for here, or we need to calculate it in a way. Either we can use the formula, the codal formula that is given, or else we can directly go for the codes. So to use the codal tables, first what we need to do, first we need to calculate the value of KL by RY, that means that is nothing but lambda, the value. Then based on that value and H by TF value, go to table number 14 where we can calculate the value of FCRB. And what is that FCRB? FCRB is nothing but the extreme fiber bending compressive stress. Now when we can calculate the value of FCRB, then based on the value of FCRB and FY from table number 13, table number 13A, so here that should be equals to 13. Here I have shown you the table, like the table is inserted here. Here 13A, we can calculate the value of FBD. So when we can calculate the value of FBD, so using this equation we can easily calculate the value of MD, that means the design bending strength for laterally unsupported case. Now then, as usual, it's a beam section, so we need to check for the design shear capacity. So the design shear capacity, that clause 8.4 of IS 800 tells about the shear capacity, and that clause said the maximum shear capacity should be, or the induced maximum shear force should be less than equals to the design shear capacity. And the design shear capacity, how we can calculate that? The design shear capacity VD should be nothing but the AV, that means the shear area, multiplied by FYW. That means the, if obviously the shear portion, that wave portion will take care of the shear, so that's why we are considering the yield strength of the wave. Or in general we can say, if we have a rolled section, that definitely will composed of, or that should be made upon a uniform grade of steel. If I use Fe 410, then I will use 410 for the wave and for the flange part. But if this case is not there, then specifically for this section FYB, that the yield strength of the wave, if different kind of plates and different kind of um, steel are used, then we need to consider specifically the yield strength of the wave divided by root 3 into gamma m naught, and this value should be greater than or equals to the factored shear force which is inducing on the beam due to transverse loading or due to loading condition. So first step, we need to calculate the design bending strength. Then we need to check for the shear capacity. And AB, what is that AB? AB is nothing but the shear area, and the shear for the different section the shear area is given. Like for the rolled section, the shear area should be H into TW. That means particularly the area of the wave is considered for calculating the shear. Obviously the wave portion will take care of the shear for that kind of sections. Now this is a flexural member and subjected to bending, so we need to check for the deflection also. So first thing, the beam which we need to design for a given set of loading. So for that beam, first we need to calculate the maximum that deflection. Say for example, if we have that simply supported beam and some loading is there, so with the loading condition and that shape and the length, we can calculate the maximum deflection value, right? So del maximum, and that del maximum should be less than your del allowable. Now how we can calculate the maximum allowable deflection limit? From table number 6, right? So here you can see for different kind of members, for different buildings also, we can easily find it out, the what should be the allowable value of deflection limits. Okay, now let's quickly solve one example so that these concepts will get clear. So first example here, I have considered that example of laterally supported and unsupported beam both, so that we recapitulate that things and we can calculate it for the unsupported case also. So what the example 1 says, calculate the design bending strength of ISLB 300 considering the beam to be laterally supported. First case, we need to calculate the design bending strength for supported case, laterally supported case, and laterally unsupported case. And assume the design force is less than the design shear strength, and this is for low shear. Okay, so for the laterally supported case, the condition for low and high shear, the low shear condition is given. Okay, otherwise we need to check, first we need to calculate the shear force, then we need to check that is it more than 0.6 time of that VD or is less than that value, and accordingly we need to design. And the effective length of the beam is given as 4 meter. Assume Fe 410 grade steel, and one more thing, and the beam is simply supported. Say the beam is simply supported. Okay, so how we can calculate? So first thing, first we need all the data. So for ISLB 300, we can get all the data, relevant data, like what should be the maximum height or depth, obviously 300 mm, what should be the width of the flange, what should be the root radius, what should be thickness of wave, and all these things. So all these data I have taken from the SP6, and as well as the moment of inertia is about both the axis, major axis as well as minor axis, and the two sectional modulus. So first thing we need to calculate the D, effective depth. So how we can calculate the D value? So on the last class, yes, actually I lost the connection. Now it's reconnecting. Yes, I am there. Wait for some time. Okay, just wait for some time. Actually, here, heavy raining is outside, so there is fluctuation in network. Okay, so am I audible? Can you confirm? Okay, so first thing, what we need to do? First thing, we need to define the section. Is it a plastic section, compact section, or other thing? So from where we can get the information? From table 2. On the last class, we did the exercise. Like first thing, we need to calculate the value of BF by 2 divided by TF, and in table 2 that is given as B by TF. So that value is well within 9.4, and D by TW is also well within 84. So if these values matches, then we can say yes, this section is a plastic section. So here we can see that for the plastic sections, the values are provided like this. How we can identify a section is a plastic, compact, or semi-compact. So on depending on B by TF value and D by TW value. And also one more parameter, that is epsilon is there. Epsilon is nothing but under root of 250 by Fy. So for our case, Fy is 250. So that become 1. So we need to check that our B by TF, that means what is that B? B is nothing but half of the width of the flange, and this value, these are well within 9.4 and 84 or not. So here we can see that yes, that values are well within that 9.4 and 84. So we can say yes, the section is plastic. Now we can easily calculate the design bending strength for laterally supported case. So for the laterally supported case, to calculate the design bending capacity, two things we need to know. One is the section subjected to high shear or low shear, high shear, or this section is subjected to low shear force. So here in this question, it is given that the section is subjected to low shear. So here from clause 8.2.1.2, we can say, and when we can say that this is the low shear when V is less than 0.6 VD. So we don't need to check for this, because already there it is given that the section is subjected to low shear. So how we can calculate the value? MD is equals to beta B ZPFY by gamma m naught. Now beta B for plastic sections and compact section, it is 1. So for our case, we have seen that our section is a plastic section. So put all these values. 1, what the value of ZP? We have considered it from SP16, and FY value. So that comes as 125.98 kilonewton meter. Now one more check is given for laterally unsupported case, that to avoid the irreversible deformation under serviceability load. So for these cases, here the code says If the beam is simply supported, then your design bending strength should be less than equals to 1.2 JDFY by gamma m naught. And if the beam is, cantilever type of beam, then you need to check for 1.5 JDFY by gamma m naught. So for our case, the beam is simply supported beam. So let's put all these values and calculate it here. That comes as 133.34 kilonewton. So what is the design bending strength? So the design bending strength MD for the laterally supported case and simply supported beam, that is become minimum of these two, minimum of 125.98 kilonewton meter and 133.3 kilonewton meter. So that comes as 125.98 kilonewton meter. Now let's quickly check for the laterally unsupported case. So for the laterally unsupported case, we will use the tables here. Okay, so on the last class we have demonstrated this problem using the formula. So now to use the table number of 14, what we need, two parameters we need to calculate first. What? That is nothing but lambda value KL by RY, okay, and the value of HF by TF. Okay, now HF is nothing but the total width of the flange minus the wave thickness. Okay, so we just considering the solid wave part. So just reduce or neglect this part. Okay, so the KL value, the effective length of the beam was given, right? The effective length of the beam, I think the effective length was given. Yes, the effective length of the beam, that means KL is given as 4 meter. Now the value of TW we know 6.7, TF 9.4, thickness of the flange, and all the subsequent values are provided here. Now we can do the calculations easily. So first thing, we need to calculate the value of lambda. So lambda comes as 142.86. Okay, so here, and H by TF value comes as the 30.9. Please check the calculations once again. Okay, if I made any mistakes, then please let me know. Now we have two values, like the lambda value 142.86 and HF by TF values. Now what we need to do to calculate the FCRB value? FCRB, what is the value FCRB? It is nothing but the extreme fiber bending compressive strength. So we need to go to table number 14. So let's go to table number 14 and look for 142.86 and 30.9. So here, this is table 14 of IS 800. So here you can see the value of lambda and the value of H by TF is provided. So here the value of lambda, in our case 142 point something is there, so 142 is not there, so 140 and 150 is there, and for our case we will consider the 30 here. So for the case of that means our value will lie within 144.8 and 160. So if we do the linear interpolation between these two values 140 and 150, of target point is 142 point something, what is our requirement for it case, so we can easily find out the value of FCRB. Or else what we will do, FCR, or during the design what we will do, we will directly consider the nearest value. Like 142 is there, we can either consider the higher value or lower value. So we are generally considering that yes, the value will be 144.8, little less, because in designing we always underestimate the value of material strength. So by this way we can calculate the value of FCRB. So what the FCRB after the linear interpolation, what is the FCRB value done? This comes as 155. You can see here, for with respect to 150, it was 144 and 160. So obviously in between 144 and 160 the value will be 155 or 56 something. So that comes as 155. Now this parameter, you can also consider that HF by TF directly 300 by 9.8. So if you do so, that provision also there in our code, that directly you can check with the overall height. Okay, so 300 divided by, yeah, 31 point something is coming. And if I consider the 300 minus, that shouldn't be 9.4 actually, that's why divided by 9.4, that comes as 30. So either way you can consider, either you can take the value of h by tf directly, or hf by tf. That means you are, neglecting the thickness of, actually that should be the thickness of wave part. Okay, please make it correct. So that comes as 31, and corresponding to that value you should calculate the value of lambda and h by tf value. Okay, so 30 and 31 point something, that will not make much differences. So now we have the value of FCRB. What we need to calculate now? We need to calculate the value of FBD. So from where we can get the value of FBD? From table number 13A. So let's go to the table number 13A, and for FCRB 155 and FY 250. FY, please make it 250. Then we can find it out the value of FBD. So let's quickly go to there. So we have 155 and Fy is 250. So here you can directly calculate the value of FBD. Like FCRB value is given here on the left side column. Here you can see, and with corresponding to Fy. So our Fy was 250, and so we need to consider this column, right, of 250, and our value of FCRB was like 155. So we have, for 150 we have 106, and for 200 we have 134.1. So directly you can consider that 106.8 for the design purpose, or else you can do the linear interpolation. So if you do the linear interpolation, you will get the value will come as 109. On the other hand, if you consider the direct value here, that value is nothing but 106.8. So there is a little difference. If you do the linear interpolation, if you go for the interpolation, that will give you the precise result, nothing else. But in the design process, it's, it's a iterative process. You need to do in, in a single go, we cannot complete the design, so we need to go for iteration. So that much of error is, allowable there. So two things here you need to check. One is h by tf value, directly go for h by tf value, and secondly the FBD value. So when you have the FBD value, now you can easily calculate the value of design bending strength. So how you can calculate the design bending strength? The formula is given on your code, that design bending strength MT should be equals to beta B ZP FBD. So FBD value you can calculate using the tables. Otherwise, you can calculate the FBD value using the set of equation which is provided on clause 8.2.2 to calculate the design bending strength of the laterally supported case. So you can see that laterally supported and for laterally unsupported case, the design bending strength is varying. For laterally unsupported case, the design bending strength is only 60.71 kilonewton meter. On the other hand, for the laterally supported case, we have seen the design bending strength is much more than the value of design bending strength in laterally unsupported case. So by this way, we can calculate the design bending strength of a laterally unsupported beams. So now, what should be the design procedure? Obviously, the design procedure should be same as laterally supported beams, but the calculation of your design bending capacity will be different. So let's quickly go to that steps. Then we will go to that next topic. So first, what do we need to do? Obviously, we are designing a beam. So first thing, we need to calculate the loads. Then we need to factorize the load in first step, calculate the total load. There can be dead load, live load combination, can be other combinations. So first thing, you need to calculate the factored load, either total factored load or or if there is a distributed kind of time in per meter, you can calculate the value. So partial safety factors we know for different combination of loads we can calculate it. Now with respect to the load, we need to calculate the maximum shear force and bending moment which is actually inducing on that section due to that load. Okay, so next step is we need to select a trial plastic section. First thing, this is a consideration that we are considering that whatever section we are taking, that section is plastic section. But later on we come to know that either the section is plastic or other kind of section. So then we do need to do the design accordingly. So we will calculate the we will calculate the required plastic modulus. Obviously for the lateral supported case also we have seen that we have calculated that required plastic modulus on the basis of yielding failure, obviously. So we have the value of md. What is that md? Md, in place of md, nothing but the maximum bending moment whatever is generated due to the factored load. That, so what we are doing in this step is we are considering that, okay, due to that bending moment, this much of plastic sectional modulus is required. Now here we are designing a laterally unsupported beam. So we need to keep in mind that there is a chance of lateral torsional buckling because the beams are not supported on the lateral direction. So what we need to do, to counteract or to eliminate the risk of that lateral torsional buckling, what we generally do, we increase the required sectional modulus by 40 to 60%. Okay, that means we are going for higher sectional modulus. And on the last class I particularly said that whatever the required sectional modulus coming, you should consider a section with higher that sectional modulus. Okay, so we can calculate the ZP value. We will increase the ZP value by 40 to 60%. Then we will select a suitable section. So if we are designing the beam using I section, so we generally prefer ISMB, that means Indian Standard Medium Weight Beam Section, or ISLB, Indian Standard Lightweight Beam Section, or wide flange beam section, and accordingly. And then we will get all the relative information of the selected section from either SP6 or from a standard that steel handbook. Now, once we have all the specifications like what should be the BF value, what should be the TF value, what should be the TW value, and all these things, then we can actually uh, identify whether the section is plastics, compact, or semi-compact. How? We just go to the table 2 and look for that what should be the value of B by TF and D by TW. Now, if these values or these parameters, lies that or tells that the section is plastic, then okay, our assumption was right, and rest of the calculations we need to do with respect to that plastic sections. Okay, so now here the table 2 is there, from where you can identify whether this section or which kind of section you are now dealing with. Okay, now what should be the next step? We can calculate, or we need to calculate the design shear capacity. So how we can calculate the design shear capacity? Already clause 8.4 I shown you that clause. Here we are if we are considering a rolled I section, generally for a beam section we have discussed the advantages of having a I section over channel and angle section. So for a I section, obviously the shear area should be equals to H into TW. So this is the design shear capacity of the section whatever you have selected for the purpose of designing that beam. Okay, Now, what is that V? V is nothing but the maximum shear force or maximum factored shear force. That means in step 2 we have calculated the maximum bending moment and maximum shear force. So this V is nothing but the maximum induced shear force due to the application of load. Now, if your design shear capacity of the selected section is more than the factored maximum shear force, then okay, the section is safe and you can go with the section. Now if that is mm, that case is violated, right, like if the design shear capacity is less than the maximum shear capacity or maximum shear force which is induced on the section, then what we have to do, we need to increase the section, or more precisely we need to select a section with higher ZP whatever we have selected earlier. Then we need to again calculate the shear capacity, and if this step passes, then we need to calculate the bending capacity. So how we can calculate the design bending capacity, we have just seen using one example. Now if that design bending capacity MD is more than the maximum bending moment generated or induced due to that application of load, then the section is okay. Otherwise, if this criteria is violated, if your factored bending moment is more than the design bending moment, then again we need to go for higher, or go for the look for the section with higher plastic sectional modulus and repeat the steps. So here, if step number 6 and step number 7 satisfied, then okay, the selection of section is done. Okay, so let's say I have selected one ISMB 400. Now that ISMB 400, okay, passes that step 6 and step 7. Now what we need to do, we need to do for checks. What checks? One is that web crippling, web buckling and deflection. Obviously web crippling and web buckling thing can occur in laterally unsupported beams also, and for laterally supported beams there also. So here, design steps for laterally unsupported beams. Okay, so now we need to go for checks. So first check, obviously the deflection check. So that for the deflection check, obviously first thing we need to calculate the maximum value of deflection. So maximum value of deflection will depend on your support condition and maximum load. So then, so first thing we need to calculate the delta maximum, and delta maximum will depend upon the load and the support condition. Then we need to calculate the delta allowable from table number 6 with respect to which kind of member we are considering. Then if delta max is less than delta allowable, then your section is okay. Now on the next stage we need to check for web buckling. So for web buckling, already we have learned how to calculate the web buckling strength. So web buckling strength can be calculated using this formula AB. So that is nothing but the area of the web. Okay, then FCD value we need to calculate. Like first thing we need to calculate the value of lambda, and based on that lambda and effective length we can calculate the value of FCD. Now we can calculate the value of FWB, and FWB value should be greater than the maximum shear force which is induced. Now last stage we need to check for the web crippling. So web crippling strength, if WC we can calculate like B2 TW Fy by gamma m naught. And what is that B2? B2 is nothing but B1 plus N2. And what is that B1? B1 is bearing length. N2 for 1:1.2, that empirical distribution, for that N2 becomes 2.5 R, or we can say R1, that root radius plus thickness of the flange. Okay, so if the beam passes that deflection check, web buckling and web crippling, and two more checks already it has passed, like the strength with respect to shear and the strength with respect to design bending strength. So if all the steps satisfies the section, or the section selected section satisfies all the steps, then we can say yes, we can go with the section, and that should be the design. So let's quickly design one laterally unsupported beam so that these concepts will get more clear. So here one example is there, that is saying design a simply supported steel joist. Now you know what is joist. So they are the beams in a steel building which supports the floors. Okay, so here we can see that part also. Now 5-meter effective span. Okay, the effective span is given as 5 meter, carrying a uniformly distributed load of 12 kilonewton per meter. If the compression flange of the joist is laterally unrestrained, then design the beam. Okay, so for design consideration, let's consider the grade of steel as Fe410, whose yield strength Fy is 250 MPa. Okay, so first step, we need to calculate the loads, or more precisely we need to calculate the factored load. So here the total load itself is given. Now if the load is given in the form of dead load and live load, so you need to calculate total load like dead load plus live load. If this combination is there, so for it you need to factor it like 1.5 and so on. So here only the total load, and we are assuming that the total load is due to the dead load and live load combination. So for this the load factor should be 1.5 because we are considering the limit state of design. So total factor load comes as 18 kilonewton per meter. Kilonewton per meter. Okay. So we need to calculate in next step. We need to calculate the maximum bending moment and shear force due to that factor load of 18 kilonewton meter. So it's a simply supported beam. We are designing a simply supported beam. So for a simply supported beam of length L subjected to a uniformly distributed load, say W kilonewton per meter. So what should be the maximum shear force and maximum bending moment? So maximum bending moment will be at the middle, and the value will be WL square by 8. So here I am considering W kilonewton per meter. Okay, per meter wise the load. If the W contains the total load like W into L, then you need to write the equation is W into L by 8. So here the factored bending moment or factored maximum bending moment maximum, this is maximum, or in step 2 calculation of maximum bending moment and shear force, maximum. And shear force, obviously the shear force will be W into L by 2, because at the supports or the reactions, the reaction force will be nothing but W into L by 2. So the shear force comes as the factored shear force or maximum. So make it like maximum. So this is nothing but your M, maximum bending moment, and this is nothing but your V, maximum shear force. Now what we need to do? We need to first, choose a trial section based on the factored bending moment and considering the yielding as a failure. So ZP required, here the formula will be M into gamma M naught divided by Fy, and this formula we have worked 2-3 example with that formula during the last session. So here M is nothing but the factored bending moment, and that comes as 56.25 kilonewton meter. So I made it Newton millimeter into the partial factor of safety with respect to material 1.1 and 250. So if you calculate it, that ZP required comes as 247.5 into 10 cube mm cube. Now what I said, that ZP required, we are only considering the moment. Now to account that lateral torsional buckling, what just a few times back I have said, that we need to increase the required plastic sectional modulus by 40 to 60%. So here we have considered that we will increase the required plastic modulus by 50%. So now what is the increased sectional modulus? So the increased sectional modulus will become or as 371.25 into 10 cube mmq. Now you have a value of ZP. Like, okay, now I need to look for a section whose plastic sectional modulus will be more than this plastic sectional modulus. So here we are, designing the beam using I section. So go to your SP6, look for the I section, start with the medium weight section. Then if the medium weight section is not satisfying your condition, then go for heavyweight section. And as per the required ZP, whatever we have calculated, after increasing it, now we need to select that section accordingly. Now while or after selecting the section, what we need to do, we need to collect all the information from that table. So here I have selected that ISLB, okay, 325. That section is primarily satisfying the value, like the value of ZPZ here is 687.76, is more than the required value. So here the overall depth H is nothing but 325 BF of this section, and all the relevant properties and the parameters I have taken it from SP6. Now we need to calculate the D value, effective depth of this thing. So H, the overall depth, minus 2 into TF plus R1, that is the root radius. So the root radius for ISLB 325, if you go and check your SP6, that is given as 16 mm. So the effective depth of the section comes as 273.4 mm. So we have selected a section based on maximum bending moment and considering the yielding as a failure, and then we have gathered the information regarding that section. Now what we need to do, we need to check whether this section is plastic or other section, because in while calculating the value of ZP required, we have considered that the section is plastic section. That's why the value of beta B there I have considered is 1. Okay, now we easily can calculate the value or classify the section. Like, we need to check for two parameters as per table number 2, that is nothing but B by TF and D by TW. So B is nothing but your BF by 2% to be considered here, and TF. So the values are, B by TF comes as 8.41, that is less than 9.4, and D by TW, that is also well within 84. And all these values you can go and check with respect to this table. Here all the values are given. Okay. So for our case also, we have considered the value of Fy is 250. So obviously the value of Xi will become under root of 250 by 250, that means 1. So okay, we have started with a beam. Considering that the section is plastic, we have selected one section and it turns out a plastic section, whatever the section I have selected. Now what I need to do, I need to calculate the value of design bending strength and the design shear capacity. So in step 4, we will calculate the shear capacity or design shear capacity of the section. So it's a laterally unsupported beam. So obviously for the lateral unsupported beams, clause 8.2.2 we need to look for. So here we can calculate the MD value using the formula beta B, ZP and FBD. So we have the value of beta B because the section is a plastic section. So beta B is 1. ZP we have, already take the value from SP6. One thing we need to calculate here, that is the value of FBD. How we can calculate the FBD value? So we will directly go to the table or use the table. So to use the table 14, first thing we need to calculate the value of KL by RY. So we have the value of RY and we have the value of effective length for the beam, that comes out 164, and HF by TF. Either way you can calculate the H by TF, that means directly 325 divided by 9.8. So obviously that will come in between 30 to 33. Now go to table 14 And with respect to 164 and 32 or 33, if you look for FCRB value, so you will get the value here. So I think, yeah, so here just find it out, like where your required values are lying. So here you can see the column here. So you just check with that values, and you can do the linear interpolation, or directly you can take the values or the nearest values. Now when you have that value of FCRB and FY, and this is a simply supported beam, that means alpha LT will be nothing but 0.21. So directly go to table 9, or more precisely go to that table 9A. Where is that table? I think I have added the table. Yeah, 9A. Now here from this table, with respect to that FCRB and FY value, you can calculate the FCD value. So now I have calculated the values here. You can check the calculations, or else you can directly take the nearest value. So the values of FCRB from table number 14 comes as 122.82, or you can directly take the initial values, that nearest values. I did that linear interpolation numerically, and FBD value comes as 93.17. So when we have the value of FBD, I can calculate the value of MD, that means the design bending strength. So design bending strength comes as 58.57 kilonewton meter. And what was the maximum bending moment? The maximum bending moment was 56.25. That means the section is okay. Now, what should be the shear capacity or design shear capacity? So the design shear capacity we can calculate using clause 8.4. It's a rolled I section. So what will be the value of your shear area? AB is nothing but H into TW. So you can calculate the design shear capacity. So design shear capacity is nothing but Fy by root 3 gamma m naught into AB. And AB is here for a rolled I beam. AB is nothing but your H into TW. So the design shear capacity is 299 kilonewton. And what was the maximum factored shear force due to the application of that factored load? That was 45 kilonewton. That means our section, that ISLB 325, I think ISLB 325, yes, ISLB 325 passes the check of um, design shear capacity and the check with respect to the design bending strength. Okay, so now two more checks are left. Three more checks are left. One is with respect to the deflection, one is with respect to wave crippling, and one is with respect to wave buckling. So in step 6 we need to calculate the maximum deflection. So it's a simply supported beam. So for a simply supported beam subjected to a uniformly distributed load of W kilonewton per meter. Kilonewton per meter. I'm using the word that yes, it is a distributed load and which is distributed over some length. So W per meter or W kilonewton per meter, and if the length of the beam is L, then the maximum deflection will be 5 WL to the power 4 upon 384 EI, and that comes as 9.4 mm. Now, what should be the allowable deflection for laterally supported and unsupported beams? This is from table number 6. We can get that the value is nothing but L by 300, and that comes as 16.67 mm. That means your delta allowable is more than your delta maximum. That means, okay, it passes the deflection check also. Now we need to calculate the wave buckling. So wave buckling strength FWB can be easily calculated by AB. That is nothing but the area, buckling area we are considering for this calculation, and the value of FCD. Okay, so assuming that the bearing length is 100 mm, that means is equals to your B1. Bearing length is important. If it is not provided, assume 100 or more the value of 100. So here B1 value is given. What is N1? N1 on the previous class we have seen that it is nothing but the half portion, neutral, the the top to the neutral portion. That means it is nothing but the overall depth divided by 2, or we can say H divided by 2. H divided by 2. So H for IS, it'll be 325. The H is nothing but 325 mm. So 325 divided by 2, that comes as 162.5 mm. So now we can calculate the value of AB. AB is nothing but the B1 plus N1 into TW. So that comes as this. And what is the I value? Why we need that I value? Because we need to calculate the lambda value for that web buckling area. So I, it is nothing but B1 with respect to that this bearing length. We need to calculate all the parameters. So with respect to that bearing length, what should be the moment of inertia? That moment of inertia comes as this. So we can calculate the lambda value and the effective length of the web. On the last class we have discussed it extensively, that what should be the effective length for the web. Then it should be considered as 0.7 times of the effective depth. So the lambda value, if we put all this, and A, what is that A? A is nothing but your B1 into thickness of the web. So lambda value comes as 90.741. We need to calculate the value of FCD, design compressive strength. So we have calculated the FCD value here. For this thing we need to consider table number C, 9C, to calculate the lambda value. So with respect to this lambda 94.72 and for FY 250, if we go and search for table 9C, the allowable stress comes as, or allowable compressive, or we can say compressive strength, that comes as 114.346. Now when we have the value of AB, AB is nothing but, what is that? B1 into TW into FCD. AB already we have calculated the AB value, that B1 plus N into TW value and FCD value. So if we plug in all these values in this equation, the FWB, that means the web crippling strength, comes as this. And during the check, what we have learned, that the design strength or design buckling strength should be greater than your design shear capacity. So yes, it satisfied the condition. So the section of ISLB 325 we have selected for our design, that passes the deflection check, the shear check, that capacity of bending moment check, and web crippling or web buckling check. Now we need to calculate one more thing, that is check for web crippling. So the web crippling strength can be calculated using this formula. So we already went through these formulas, like considering that 1 is to 2.5 empirical load distribution formula, the FCW strength comes as, this is nothing but the area into Fy by gamma m naught. Now how we can calculate the BT value, B2 value? B2 is nothing but B1 plus N2, and N2, this is, we can calculate considering that 1 is to 2.5 load distribution. So we can calculate this N2 value as 2.5 R1, that is the root radius, plus thickness of the flange. So B2 value, all the values are here. So B2 value we can calculate. First we need to calculate the N2 value. N2 comes as 64.5, like R was 16 mm, TF was 9.8 mm. And now we can calculate the BT value. So B1 we have considered as 100 mm plus N2 comes as 64.5. Now plug all these values in this equation. You can easily calculate the value of web crippling strength. So the value of web crippling strength comes as this, and obviously this should be greater than equals to the design shear capacity. So the design shear capacity was, I think, 202.5. sorry, 299 actually, 299. So either way we can check it for the design share capacity. Okay, so here 202, I have written here 202, but the 202 value should be not there. Let me check here once again. So we need to check against the maximum shear capacity. Okay, greater than V, the maximum shear capacity we can check, because the design shear capacity it's the inherent property. So we need to check against the maximum factored shear force. That means 45. So here also that should be greater than this. So nothing but 45 kilonewton, and also here also 45 kilonewton, because that Vd is nothing but that inherent design property, like this is the capacity of the section, and that V is the nothing but the demand portion. That means that is the factored force which is generated due to that load. So basically we need to check against the factored shear force which is generated due to the maximum loading. Obviously that means we need to check with respect to demand, not the capacity. So obviously that should be greater than 45. Okay, and these two checks, the two strength are also well within that limit or much more than that 45 kilonewton. So we can say that okay, this beam section is safe against your wave buckling and wave crippling thing. Okay, so this is the design procedure of a laterally unsupported beam. So what was the design procedure? Let's quickly summarize these things and please check the calculations. Okay, I may made some mistakes on calculations. So what we have done here, so let's quickly recapitulate it, then we will go to the next section. First thing, in a first step, the design of every beam, we need to calculate the loads. Then with the respect to that factored load, we need to calculate the maximum shear force and maximum bending moment. Now when we have the value of maximum bending moment, we need to choose one suitable section. How we can choose it? We need to calculate the required sectional modulus. Now the required sectional modulus is based on the maximum bending moment and considering the yield as a failure. Although for the laterally unsupported case, to counteract that lateral torsional buckling thing, we need to increase the required plastic sectional modulus by 40 to 60%. Then whatever section we have selected, we need to check this section you know lies under which class. Is it a plastic section, is it a compact section, or a semi compact section? Then when we have done the classifications, we need to calculate two strength: design shear capacity, design bending capacity. So design shear capacity we can check using clause 8.4, and obviously your design shear capacity should be more than the factored shear force which is generated. Now we need to similarly we need to calculate the design bending capacity, and the design bending capacity should be more than the design or the factored bending moment, maximum factored bending moment. Now if these two steps or these two checks passes the section whatever we have selected, then we can go to the next step. Otherwise we need to select a section with higher sectional modulus. Now if when these two checks are completed, we need to go for the deflection check, wave buckling and wave crippling thing. If all the steps the selected section can complete all the steps successfully and pass the all the checks, then we can finalize the design that okay, we need to select this and we need to go with that section. Okay, so now we will spend some time on learning how to calculate a plastic sectional modulus about different axes. During design, this part is also needed. How to calculate? Sometimes you need to calculate that plastic modulus about y-axis. Sometimes you need to calculate it about z-axis. So let's spend 5 to 10 minutes on this section. Then we will go to the design of purlins. So it's nothing but it's a we have learned these things on strength of material or solid mechanics on third semester. So it is nothing but what is ZPZ? That means the plastic sectional modulus about the ZZ axis. So here you can see, if we consider this is a ZZ axis, say ZZ axis for a particular section, and say let's say this is your YY axis. Y, Y. Now first thing, two plastic sectional modulus like about YY and about ZZ we need to calculate. So first let's see about ZZ. So here you can see from this diagram the ZPZ about ZZ axis. What do we need to do here about ZZ axis if we need to calculate the value of ZP? So nothing but we need to calculate the area of the top portion and the distance of center of gravity, CG distances. Like now, if we can calculate these two things, just multiply it with 2. Like here also this portion is there. So we can calculate the ZPZ or the plastic sectional modulus about the ZZ axis. So here you can see for the flange portion, this is the value. So this is nothing but the area B into TF for both sides, and this is nothing but your CG distance H minus TF by 2, and this is nothing but your HF, what I was talking about earlier. Now one more thing is left when we are calculating the ZPZ or plastic sectional modulus about this axis. One more thing is left, this area or this area. So if we can calculate the area and CG distance of the area above the neutral axis, then just multiply it to. So this is the area of this section and this is the CG distance from your center of CG and multiplied by 2. So if we simplify the equation comes as BF into TF multiplied by H minus TF plus TW multiplied by H minus 2F square by 4. And if we plug all the values in this equation, we can calculate the ZPZ value. Now how we can calculate the ZPY with respect to Y value? So here from this figure you can see, if we need to calculate the sectional modulus about this axis, so what do we need to calculate? We need to calculate the area and CG distance of these 4 portions. 1, 2, 3, 4. Right? So what is the area? Area is nothing but BF by 2 into TF. Okay, BF by 2 into TF multiplied by the CG distance. The CG distance will be nothing but BF by 4. Okay, now multiplied by 4. Why multiplied by 4? Because we have 4 sections like 1, 2, 3, 4. So for this 4 section about Y, we have calculated the area and the CG distances from here to here. So that comes as this part. One more thing is left, that is that portion, the wave portion about YY axis. The flange portion we have made the calculation. Now for the wave portion. So the wave portion, this is the area and this is nothing but the CG distance. So if we simplify this, the ZPY about Y axis, the plastic sectional modulus comes as TF into BF square by 2 plus H minus 2 into TF TW square divided by 4. Either you can remember these formulas, or you can easily calculate it using just first moment of area formula, or easily it's like not the rocket science. Okay, so here one example is there, like here the I section is one I section is there, and the relevant properties of that I sections are provided, like the overall depth of the I section is provided, the overall depth is provided, like H is equals to 300 mm, BF and all these things are provided. Now you can calculate the ZPZ, like BF into TF multiplied by H minus that simplified formula of the previous slide. So that comes as this, and if you plug in all these values in this equation ZPY, subsequently you can calculate the value of the plastic sectional modulus about y-axis. So these two things might be required during the design. If for a particular section you are unable to find that value of plastic modulus about z and y-axis from that sp6, then you can go or use this set of equations to calculate the value of required plastic modulus, or plastic modulus about z and y-axis. Okay, so it's all about calculating the sectional modulus. It's like the calculation of moment of inertia about this axis, and all these things. Okay, so let's go to the next topic. Okay, so till now, I think there is no confusion. Now, Purlins. So we will spend some times on Purlins, how to design them. This is one of the important structural element in roof truss. So what is Purlin? Purlins are basically the horizontal flexural element of a roof truss. Here from the picture you can see like these are the purlins. This that horizontal beams you can see on top of the rafter. Okay, so let me explain it one by one. So this portion, this inclined part of a roof truss, this part is called the rafter, and above this rafter the purlins are you know placed longitudinally, and on the top of the purlin the you know that corrugate sheet or the that cover sheets are provided. So basically here you can see the top view of this section. So here the purlins are aligned like this and placed like this with some spacings. Okay, the thing is obviously they are flexural member. Now why flexural member and which kind of load they are subjected to, we need to now look for it and design it. So first thing, one thing, the purlin. What is the purlin? Purlin is nothing but the horizontal flexural member of the roof truss. Okay, one two specifications of purlin, like the purlins are designed or analyzed considering a continuous beam slash analyze considering considering a continuous beam. One thing. Second thing, the purlins are subjected to biaxial moments. That means they are subjected to load from both the direction, parallel and perpendicular direction. That means they are subjected to biaxial bending. They are subjected to biaxial bending. Okay, so let's start it from the basics. Say for example, this is your rafter. Okay, so rafter, obviously that will be placed with some inclination angle theta with respect to the horizontal. Now the thing is, the purlins are placed over the rafter. Generally the channel section, I section and angle sections are used as a purlin. So like this, if the one channel section is there, so channel section, why I'm considering the channel section, because in your course the channel section is considered. So in align with that, the channel section, like the channel section are provided like this on the reverse direction. This is preferable, and the angle, this is connected with some cleat angles. The design of cleat angle we have already covered earlier. So this is the clit angle. Now the thing is, first thing what I have said, that they are subjected to loads from both the direction. That means if we consider the direction, say for example, let's say this is the, say we can consider this is ZZ axis or XX axis with respect to your that particular member, or we can have here a new reference axis. Like we can say, okay, this is UU. Let's consider this is UU. This is nothing but the, what is that? That is nothing but the ZZ axis of this particular rolled section. Okay, UU, and the YY axis, let's consider this is VV axis. V. Okay. Now the load. What about the loads? First thing we need to understand about the loads. So for loads, which kind of load can come to the purlin? So first thing, wind load. Obviously they are subjected to winds, and it is considered that the wind load is applied, you know, perpendicular to the roof. Okay. So now let me clear it and draw it correctly. So draw it, actually clearly, so that we can understand the load distribution part. Okay. So this is like VV. For now, consider the VV and UU axis, or else you can directly consider that UU axis is nothing but the ZZ axis with respect to the rolled section, whatever we are using here. So if we are using the channel sections here, like channel sections are placed like this, and other sections I will come into it later. So first thing, what is the load? The horizontal load due to wind. So wind are, you know, assumed to act perpendicular to the roof. So that is, say for example, this is wind load H. And one more thing, the dead load of the purlins, gravity load, and all these things, they generally act they are act vertically downward through the CG of the member. Okay, so two main force is coming. One is horizontal force due to wind, and they are considered that they are acting perpendicular to the roof, and one is that, self weight, gravity load, and all other loads, snow loads, that's all load are, considered that they will act, vertically downward. Now the question is, here we have two axes of the purlin. One is that UU axis of the purlin member. This is nothing but your ZZ axis. You can, consider it is ZZ also, so that there will be no confusion. And VV, it is nothing but your YY axis of the main member. Now the thing is, what should be the, component of force acting along this direction perpendicular to the roof, and one is that along this direction? What should be the magnitude of load along YY and along ZZ, or I can say along VB and along UU? So what should be that? So if I consider that this is nothing but your P dashed value. So P dashed, what is that P dashed? P dashed is nothing but the total component of load which is acting perpendicular to the roof, or we can say the total component of load acting along the YY axis of the purlin. So what will be that? If this is theta, then obviously this will be theta. So what should be the value of P dash? P dash will be equals to H. That means the force due to the wind, or horizontal force due to the wind, plus the component of P. Which component of P? That is P cos theta. Now what should be the value of that force acting along this direction? Say, let's say this is nothing but H dash. So what should be the value of H dash here? So H dash will be nothing but P sin theta. Okay, so this angle will be theta. If this is theta, so this angle will be theta, this angle. Okay, so by this way we can calculate the load along two axes, along, parallel and perpendicular to the roof of the uh, or roof, or we can say the loads with respect to your UU axis and load with respect to VV axis we can calculate. So now two kind of loads are acting. One, the load acting along UU axis, the loads acting along this UU axis, and the load acting along the VV axis, or we can say the loads acting along, YY axis and XX axis. So what should be the maximum bending moment? So I have already told you that the purlins are considered as continuous beam. So the bending moment about UU axis will be equals to P dash L by 10, and where the P dash value I have already calculated here, that the value of load which is acting, say for example, if this is the rafter and a channel section is used as a purlin, the clit angles are generally provided here. Okay, so we have one axis like YY axis of this, whom we call the VV axis with respect to your purlin, and that UU axis. So what is that P dash? That P dash is nothing but the load coming with respect to that your UU axis, sorry, VV axis, and if we consider this is UU axis, so correspondingly the load will come with respect to this axis. So total H dash is nothing but the horizontal load, so this is your H dash, and this is nothing but P dash. So P dash, we have calculated P dash is equals to H, this is the horizontal load due to wind, plus P cos theta. What is theta? The inclination angle of the rafter or the roof. So here we can see this is P. So if this is theta, then obviously this will be theta, and subsequently we can calculate the value of P dash and H dash. So when we can calculate the P dash and H dash value with respect to the gravity load, self weight and wind load, P sin theta. So when we can calculate all these values, now put all these values in these equations, like what should be the maximum bending moment about UU axis, obviously that about UU axis, about this axis, and about VV axis. So this one was the VV axis, or more precisely, don't fall in the confusion trap of VV and UU. Just consider this is your ZZ axis of the main member, and this is the YY axis of the main member, and just stick to it. So first step should be the load calculation or moment calculation. So MU nothing but your MZ is equals to, and this is the induced, and My. equals to H dash L by 10. Now, what is the P dash value? P dash is nothing but the loads acting, or the net, or the resultant force acting, along the YY or along the VB axis. Obviously, that will produce the moment about UU axis. Okay. Now, when we have the value of MB and MU, now in the next step, we need to calculate or check for, that combined bending, because this is subjected to biaxial bending moment. So we need to check with respect to the interaction formula. So what that interaction formula says, that for a biaxial bending, we need to check for that mu, or we can directly write mz divided by mdz. That means this is the maximum bending moment with respect to or about zx, and this is the design bending moment about z axis, plus my by mdy. That value should be less than equals to 1. Okay, this check is important because the purlins are subjected to biaxial bending. The next stage, we need to calculate the value of required sectional modulus, because we need to select the section. Now, what should be the criteria for selection? Because on the laterally supported and unsupported beams, we have seen that the selection of the section criteria is depends on the mz, because only one moment is there, but here the biaxial bending is coming here. So the expression for calculating the required plastic modulus during this course, so we provide or we prefer the formula of Gallard et al., which is published at 1992, and generally this formula is used to calculate the selection the required section of purlin, or more precisely to calculate the required plastic sectional modulus. And what that formula says, that formula, you need to consider the moment about two axes, mz and my, both the axes. With respect to both the axes, you need to calculate or consider the ZPZ. So to calculate the ZPZ value, mz gamma m naught by fy multiplied by my gamma m naught by fy. Two things about z and about y, both the axes we have considered, multiplied by 2.5 d by bf. Okay. Now, initially, neither the d and bf, these two parameters will be unknown because we are selecting the section. So first thing, for a trial section, we need to consider first the D and BF value. Based on that, we need to calculate ZPZ, and then we need to check for it. Okay. Now, when the required ZPZ is calculated, now we can go for next step. So basically, what are the design procedures? So what I've said, that we can use like channel section as a purlin, we can use I section, we can use angle sections as a purlin. So generally, this is the channel section. If angle sections are there, so generally the placing of angle section is like that. So this is the main angle, and this will be connected by a cleat angle like this. So this is the angle configuration. Even we can use I sections for it also as a purlin. So generally, for I section and channel section, the design procedure is different, and for angle section, the design procedure is still different. So firstly, we will see what should be the design procedure of purlins when we use the channel or I section. So for this I section, this cleat angle is like here. Reverse cleat angle should be provided like here, like this. The reverse cleat angles are provided. So the thing is, we need to know about the loads, the two load, one, the load which is coming, if we are considering the axis as reference frame, that P dash, the coming to the purlin with respect to the YY axis, and the load from that horizontal side or with respect to the UU axis. Now, while we have calculated the loads, we can calculate the moment, because the purlins are basically designed as a continuous beam. So WL by 10, where look here, that P dash and H, these are the total loads. Okay, these are the total loads. If they are distributed, uniformly distributed per meter, then that will be P dash into L square by 10 or H dash into L square by 10. So please take care of the values, like is it a total load or is it a per meter distributed load. Accordingly, you should calculate the moments. Okay. So first thing, we will look for the design procedure of a purlin when we use channel or I sections. So when we use the channel and I sections as a purlin, what should be the design procedure? So first thing, obviously, we need to calculate the span or length of the purlin. It is generally taken as the center to center distance of the adjacent trusses. Okay, that means the spacing should be provided there, and number of bays and number of either number of purlins or number of bays will be provided. Based on that, we can calculate the center to center distance of this purlin. Next step, when we have calculated the length of the purlin, now we need to calculate the loads. One load which is coming with respect to your YY axis, and one load which is coming with respect to ZZ axis. Two loads we need to consider. Or either we can say this is, if this is your UU axis, so we need to consider the load along this UU axis, that is nothing but H dashed. And one thing, we need to calculate the load with respect to this VV or ZZ axis. So this is nothing but P dashed. P dashed. Okay. And if we know the inclination angle, so we can calculate it using, like, P is the factored load due to self weight and all these things, and H is nothing but the value of wind load. So we can calculate the value of M Y and MZ simply, or MU, MB and MU. Now maximum bending moment and shear force are determined. Next stage, we need to calculate the required sectional modulus. Now to calculate the required sectional modulus, first thing we need to start from a basic section or considering some section, like these two parameters of that ZPZ formula. These two parameters are unknown, still unknown. Then let's start with some B and TF value. Then we will check, or we will select the section based on that initial B by TF value, whatever we have selected based on that some section. Now we need to check whether the section or which kind of section is this. Now we need to check for the shear capacity in both the directions. Shear capacity in both the directions, because here this section is subjected to loading from both the directions. So obviously we need to check the shear with respect to both the axes. Okay, so this is, if this is ZZ axis and this is YY axis, so we need to check the shear capacity with respect to ZZ axis. So for ZZ axis, it will be nothing but Fy by root 3 gamma m naught AVZ. And what would be the AVZ about ZZ axis? It will be nothing but 2 into BF multiplied by TF, thickness of the flange. With respect to ZZ axis, if we see, then obviously the BF portion here and the BF portion here and the thickness of the flange, if we multiply it, then we can calculate the area. That means the area of the top portion and area of the bottom portion. And what should be the AVY? We need to calculate the area of this wave portion. So H into TW. Okay. So here, what is that? H is the height of the section, not D. H is the height of the section, TW thickness of the wave, BF breadth and width, all these things. So we need to check that VDY and VD both are, more than the shear capacity or the factored shear force which is coming along Y and Z direction. When we have calculated this step, now we need to check for, first we need to calculate the design bending strength along both the direction, along Y direction and along Z direction, because these purlins are subjected to loading from both the directions. So MDZ, obviously about Z axis, that means if when we are considering the moment or the moment capacity about this, say for example this is your ZZ axis of the member, obviously this is the ZZ axis of the member and this is the YY axis of the member. So when we will calculate MDZ, we need to consider the plastic sectional modulus about ZZ axis. Now how to calculate the plastic sectional modulus? We have seen the formula, and also these values are available in code. Now for the simply supported case, we need to check that yes, for and these are, the design bending capacity is considered using the laterally supported beam condition. So for the if you recall that our code says the design bending capacity of this section should be checked against that 1.2 Z EZFY by gamma m naught. Now about y axis, we can calculate ZPY with respect to ZPY, and they should be less than this. Now when we have two values like MDZ and MDY, and also we have the two factored moment like MU, or that is MZ, and MV or My. Now when we have these four values, now using the interaction formula, we can check either the biaxial bending capacity or the biaxial, you know criteria is satisfying or not. So how we can calculate it? Using that interaction formula. Now when this check is passed, then we need to check for the deflection limit. So deflection limit, how we can check? So deflection limit for table 6 and for the purlins, for table 6, if we look closely for the purlins, we can see that the deflection limit for the purlin is nothing but the L by 180. Now if the purlin or the section we have selected for designing the purlin, if this is um, passes all the checks, then we can say that yes, that I or channel section whatever we have selected, this section is suitable for designing the purlin. So this is the design procedure of purlins when I and channel sections are used. Now when angle section are used, the design procedure is little different. Like here we can see. Okay. So for angle sections, what we need to do? First thing, obviously, we need to calculate the loads, the vertical and that horizontal loads. And one more thing, for this section, angle section, what is assumed here, that all the loads are assumed to be normal to the roof. That means we are ignoring the part of horizontal load here. So like your UU axis, we have some loads, and about your VV axis, we have some loads. Like recall, this was P dash for the channel section, and this one is for H dash. So now here, when we consider the angle section as a purlin, so for this case, we considered that all the loads are assumed to be normal to the roof truss. Now we have only one directional load VV. So obviously we will have the moment about ZZ or about UU axis. So how we can calculate it? WL square by 10 if that W is, uniformly distributed load, say something W per meter, and this W is total load. Okay. So here, what is the basic change? So for here, we can see that the moment is, entirely we have considered about that UU axis of the Purlin or ZZ axis of the member. Now the required modulus we need to calculate using this formula. This is an empirical formula. So to do so, on the next step we need to assume some depth like 1 by 45 and width 1 by 60. These are the general you know consideration of designing this section. Then with respect to that ZPZ and depth and width, we need to select a suitable section. So let's quickly solve one example, okay, of Purlin, so that this concept of design of Purlin it completed. Okay, so let's quickly solve it. So here one example, read it out. What that example is saying, the design an I section Purlin. Okay, so here for the example we are considering the I section Purlin. So we have went through the design procedure of design of Purlin using I or channel section. So what said, design an I section Purlin for an industrial building situated in outskirts of Kolkata. Now why Kolkata is important? Because to calculate the wind load we need to know the zones. To support a galvanized iron sheet roof for the following data. Okay, the slope is given 30°. That means the rafters are placed at angle of 30°. So this is the total roof truss, and I sections are used as purlins. Okay, so this is 30° spacing of truss. Okay, spacing of truss is given 5 meter. Span of truss is given is 12 meter. Spacing of purlin is given 2 meter. That means the spacing is needed. Wind speed is given 50 meter per second. Now to calculate the dead load of the galvanized sheet, the weight of the galvanized sheet per meter square value is given as 120 Newton per meter square. Grade of steel, for design consideration we need to consider as Fe410. So what should be the first step? The first step should be the load calculation. The step 1 should be the load calculation. Load calculation. So first thing, weight of the galvanized iron. So here per meter square is given 120 Newton per meter square, and the spacing of purlin is 2 meter. So obviously for per meter length you need to consider calculate it. So 120 multiplied by 2, that means 240 Newton per meter. Okay, now dead load of the purlin is not given, and we also don't know the which kind of section we are going to design. If we know the road section, then we can calculate the weight of the road section subsequently. But here for the design purpose, let's assume the dead load of the purlin is 100 Newton per meter. So what will be the total dead load? Dead load of the galvanized iron sheet plus dead load of the purlin, that is 340 Newton. So this is acting, vertically downward. So here, this is nothing but your P value. This is nothing but your P value. Okay. So what should be the vertical and horizontal component? So the component of dead load parallel to the roof, that means this component, your so-called H dash component, what will be that? That will be nothing but 340. That means the total load P, that P, whatever we have calculated, P multiplied by sine of 30 degree. So that comes as 170 Newton per meter. Now what should be the component of this load with respect or normal to the roof? That means this component will be nothing but P into cos 30. Why we need that component? Because the total load P dash along this axis will be equals to H. That means the horizontal load due to wind plus that normal component of load to the roof. That means your this value 340 cos 30 degree. That means nothing but P dash equals to H plus P cos theta, whatever we have learned. Now H, still the value of H is unknown. What is that H? This is the wind load which is acting normal to the roof. Now here the for zone Kolkata zone 0.6 we have found out the zone factor, and Vz, that is the wind speed, design wind speed, or we can say this is 50 is given. So the wind pressure comes as this. So what should be the wind load? So for the roof, I have already told you that wind load is assumed to act normal to the roof, normal to the roof. So per meter, if we need to calculate the wind load, this is the wind pressure. So per meter, that means the spacing of the purlin is 2 meter, and we are calculating the per meter area. So what will be the total wind load now acting normal to the roof? That means this H value. What should be that H value? H value should be nothing but the wind pressure per mm square multiplied by the spacing multiplied by 1 meter. That comes as 300 Newton per meter. So total load, normal load to the purlin, that means the P dash value will be equals to H. That value is H, that part is H, and this part is nothing but your P cos theta. So total load this. Now we need to calculate the factored loads. So here we can calculate the factored load with respect to both the directions. So here instead of P dash, I have written P here. So you can write it down like P dash is equals to 1.5 times of the load normal to the roof, and this is your H dash. So now we can calculate the maximum moment mu or mz. That means with respect to that uu or zz axis, whatever we want to assume the axis here. So with respect to this and with respect to this, we have two loads. So with respect to, say for example, this is u slash z axis, u slash z axis, this is v slash y axis, v slash y axis. Now either way, either you can consider the vv axis or yy axis. So what should be the moment with respect to zz or uv axis? It is nothing but p dash. Say if we are considering the P dash is the total load acting normal to this is P dash, and this is nothing but your H dash. Okay, so my, subsequently we can calculate it like H dash into L upon 10. So the moments about 2 axis we have calculated. What should be the next step? We need to select one particular section, and the selection criteria is based on the moment about 2 axis and with some empirical formula referred by Gallard et al. Now let's say here in this formula these two parameters are unknown, say d by bf, or more precisely we don't know the d value and bf value. So for example, let's tie with a flange width of 75 mm and d of 125 mm. So if we use these two data, now we can have a value of required plastic modulus as 66 point or 66 into 10 cube mm cube. Now let's go to the SP6 and check whose, a section whose plastic modulus is more than this, and the flange width we have considered that this is near about 150 mm. So here 75 mm, sorry, the flange width is considered as 75 mm, so near about 75 mm look for the bf and whose plastic modulus is more than this. So if you go and check the SP6, you will find out that ISLB 150 have a sectional modulus 104.5. So we have considered this, and a BF. The width of the flange is 80 mm. So we have considered BF as 75 mm. So this value is near about this 75. So now, okay, we have selected one section ISLB 150, and that will be used for the purlin, or used as a purlin. So for the section, the subsequent values like area, what should be the cross-sectional area, what should be the overall depth or age, what should be the BF, what should be the TF, and all these values we have calculated from there. Now precisely we can calculate the value of effective depth. What should be the effective depth value? This is nothing but H or D. Here you can see H or D minus 2 into R plus TF, or TF plus R1. So the value of D effective depth comes as 117.4 mm. Okay. So here we have selected the section, and we have collected all the data which will be required for the section. Now what we need to do? We need to check that under which uh you know section class it is falling. Then we need to check for bending strength and shear strength on the both the directions. So first thing, we need to calculate the value of BF by 2, or directly from table 2 we can we have already seen that B by TF we need to consider this value, and B is nothing but BF by 2, directly consider that value. So these are this value BF by 2 by TF is less than 9.4, and D by TW is less than 84. So we can say this is a plastic section. Okay. Now we need to check for bending strength. How we can calculate the bending strength? MdZ, already we have seen that ZpZ with respect to Z and with respect to Y we need to calculate both. So dz is nothing but ZpZ. We already have the value of ZpZ, we have the value of Fy, and this comes as 23.75, and that should be less than equals to this as per code. So obviously that comes as 25.04 kilonewton. And what was the MD value about that Z axis, or induced moment value about Z axis? So that was 12.35 kilonewton per meter, 12.35. So obviously the value of design capacity is more than the induced moment, so obviously the section is okay. Subsequently you need to check with respect to the y axis. So for MDY you need to use ZPY into Fy by gamma m naught, and you need to check that this should be less than this, and also MDY value should be greater than your y value, and my value I think comes as 0 point something, 0.33 or something. So I have checked the values, and this values is also satisfying the condition. So you do the calculation for one y axis. You have leave the calculation up to you. So here, okay, so here I have calculated this part also. So let's go to it quickly. So m dy. So for dy, we need to first calculate the ZPY value. That means the required plastic modulus about y axis. So how we can calculate this? We have seen earlier that using this formula, or either way, or you can directly draw the section or calculate the ZPY. That means nothing but the plastic modulus about y axis. So m dy, that ZPY comes as 2256 mm cube. Now put all these values in MDY equation. That means the design bending capacity with respect to YY axis or VV axis. So that comes as ZPY into Fy by gamma m naught. And we need to check for that. Here I have replaced that 1.2 with 1.5, because here the the checks, I want to carry it out with respect to the Orr's condition, or the limiting condition. Is it satisfying or not? And you also can go for that 1.2 checks. That is also. So here from these slides we can say that your MDZ is more than MZ, and your MDY is more than MY. That means the section is safe against the bending strength. Now we need to check for the shear capacity and deflection capacity. Also we need to check for the combined effect of this. So first thing, using the interaction formula, first thing we need to check for combined that bending moment, the bending moment with respect to x-axis and with respect to or x here z axis, and with respect to y axis. So using that interaction formula, that mz, that means the induced bending moment about z axis, this is the design bending moment about z axis, this is the induced bending moment about y axis, this is the design bending moment. So induced bending moment we have already calculated, design bending moment on the last slide we have calculated, and this values comes as 0.66, well within 1. Then hence this is okay with respect to combined bending moment. Now we need to check for deflection. So we are designing a purlin. So limiting deflection value of purlin is given as L by 180 in table number 6. So allowable value, the effective length of the purlin was given as 5 meter. So that comes as this. And here for the simply supported case, we are considering this formula. Here for a continuous beam, we are considering this formula, and this formula is coming as del is WL to the power 4 divided by 384 EI, and this comes as 4 mm. And this is also well within the allowable deflection limit. That means this is nothing but the delta maximum value, and the delta maximum value is well within the delta allowable value. That means our design with respect to that ISLB, or the section we have selected here, like we have selected ISLB 150. That means yes, we can go with the ISLB 150 for the design of the purlin. Okay, so that was for now. Gantry girder we will start on the next session. So let's quickly solve some example previous year examples. Okay, so let's quickly solve it. So read it out, the first example. Question number 1 says, in the design of purlin or design of angle section purlin subjected to uniformly distributed load, what should be the maximum moment? So for angle section, what we have seen, that we are considering all the load perpendicular to the roof. So obviously, and it is a continuous beam. So that will be nothing but WL square by 10 if that is W is load, uniformly distributed load per meter, and if the total load is given, then W into L by 10 will be the value. So the option B will be the correct answer. Now let's go to the second question. What is the additional vertical impact load for hand operating cranes? Okay, so we haven't go through that, but still, for the purpose of solving the question, actually the 10% of the maximum static wheel load is considered for hand operation cranes. So option B will be the correct answer. Now, what is the maximum permissible vertical deflection limit of the gantry girder having span 6 meter when the electric overhead traveling cranes is operated at 40 T or 45 T? Okay, so for this calculation, first we need to calculate the maximum deflection of electric overhead cranes. So this is nothing but span upon 750. Now if we know the span upon 750 for 45T and for 50T, so that comes as span is given as 6 meter, so 6000 divided by 750, that comes as nearly 8 mm. So 8 mm will be the right answer. Now let's go to the next question. Here, the required plastic sectional modulus for angle section. So for angle section, the required plastic sectional modulus can be calculated using this formula. ZP required is equals to M by 1.33 multiplied by 0.6 into Fy. Now, let's see the next question. The maximum deflection limit for Purlin. The maximum deflection limit for Purlin as per table 6, that is span by 180. Now, what is the next question says? Okay, so here we need to calculate the value of ZPY, I think. Okay, so determine the plastic sectional modulus about the strong and weak axis respectively. So strong and weak axis means for a section, say here I section is given. So for a I section, what is the strong axis? Obviously the ZZ axis. So you need to calculate the required sectional modulus with respect to that ZZ axis and also with respect to that Y axis. So we have already seen how to calculate the required sectional modulus about Z axis. And if we simplify this equation, so this equation stand out to be BF TF under bracket D minus TF. D is nothing but that overall depth into TW D minus 2TF square by 4. Now put all these values in this equation, you can calculate the ZPZ value and ZPY value. The equation for it, we have already seen. The simplified equation comes as TF into BF square divided by 2 plus B minus 2TF divided by 4 into TW square. Or else we can calculate about, for calculating the about ZZ axis, we need to calculate the area of this portion and CG distance multiplied by 2 plus area of this portion into CG distance multiplied by 2. That's all for ZZ. And for YY axis, that 4 flange portion, 1 2 3 4 4 flange portion will be there, and half of the wave portion we need to consider for this portion. So using these two equations, you can easily calculate the value of the required plastic modulus or the plastic modulus about ZZ and about YY axis. That means about the weaker axis and about the stronger axis. Now, next question. Okay, so this is the design of Purlin. So we have just solved one example regarding this. So please go to the example. You can easily find it out here. What is the difference? The slope at that example, the slope was 30 degree. Here the slope is 26 degrees given. Spacing of the truss is little bit different. So the process is given like first we need to calculate the weight of the galvanized steel, that is per meter square value 95 multiplied the spacing of the purlins. Then dead load of purlin is given. The dead load of purlin is given. So dead load of purlin is nothing but 115. So total dead load coming as this. So total dead load means that P value. So what should be the normal component and what should be the vertical component? So if I draw this and look for the component, so we can see it. So this is the rafter portion. This is the inclination angle of rafter with respect to the vertical portion. And if the purlin is here, say let's say a channel section I am using as a purlin, so it has a axis here and here. So the load P, that means the dead load, this will act, vertically downward to the CG. So this is your P. Okay. So what should be the horizontal component and vertical component of P? We can calculate with respect to the theta. So the uh, the dead load normal to the roof will be P into cos theta, and the load parallel to the roof, that means this load we need to calculate this H dash and total load P dash. And here also according to that direction or perpendicular to the roof, wind load is also coming. So this is the P. First thing, we need to calculate the horizontal and vertical component of P, or more precisely parallel and perpendicular component of P to the roof truss. So they are coming as this. Now what is the value of H? The wind load. So wind load we can calculate it like the design wind speed is given as 45 meters square. So this will be nothing but 0.6 multiplied by 45 square. This will be H. So total perpendicular component, what will be that? P dash will be nothing but H plus P cos theta. So here you can see the value. Normal load to the purlin here. Then we need to factor it out with 1.5. And what should be the H dash value? H dash value will be equals to P sin theta. So here you can see factor load along the roof H. So here they have used H is equals to 1.5. Now we can calculate the value of mz. Mz will be nothing but P or P dash. I have used here P dash into L by 10. And what should be the value of my is nothing but P or H dash, here H dash into L by 10. By this way you can calculate the value. So the values are coming as mz 15.184 and my comes as 0.677 kilonewton meter. So I think which option you just look for it. I think option B is the correct answer. Now let's go to the next question. Okay, maximum shear force in a gantry girder carrying an overhead traveling crane. Okay, for this, one of the wheel load at the support we generally need to consider. So option A will be the correct answer. Now calculate the normal fatigue range and shear fatigue range respectively for a gantry girder for a given data. Okay, so for a given gantry girder, so how we can calculate the fatigue strength? Okay, fatigue range. So basically we have the formulas for it. Like first we need to calculate the actual number of stress cycle. How we can calculate the actual number of stress cycle? So the values like the maximum 3 trips per hour is given. Now how many hours? The hours is also given. 8 hours. Okay, these 8 hours are given and 250 days is given. So just multiply it with this, so we can calculate the stress cycle. Once we have the stress cycle, the f and tau f value, that means uh, the two values corresponding to the fatigue range, normal fatigue range and shear fatigue range, we can calculate using this formula, like fn cube root of 5 into 10 to the power 6 by NSC and all these things. So the values are coming as 150.70 and 103.56. So the option A will be the correct answer. Okay, so that's all for now. So what we have today learned, let's quickly summarize the things, then we will conclude here and we will meet on the next class. So first thing, we have learned how to design a laterally unsupported beam. Laterally unsupported beam. Then we have learned the design of purlins and how to calculate the plastic modulus about z and y axis. And thirdly, we have solved the previous year assignments like 2020 assignment. So I am planning actually took an extra class where I will elaborate different or discuss different year that assignments. Like I have the assignments of 2020 and 2019. So on the last class, on the 13th interaction session, I will discuss that different year assignment solution, or the possible uh, the question papers, how that will be set. So and all these things we will discuss on this class. Okay, so if you don't have any questions, then we can conclude here. Okay, so thank you, good night, we will meet on the next interaction session.